And I showed the bigger pulley first. And so let me go to the far extreme and go to the smaller pulley. Now, let me just lower this down a little bit so I can get to the low one. But here's what I want you to see. I'm going to put the same weight on here, so it's the same amount of force. But as I come over here and look at this equation, even though it's going to be the same force, it's going to be wrapped on a pulley that has a smaller diameter. In other words, it has a smaller lever arm. And I'm claiming that I'm going to get a smaller amount of torque. Not because this is a smaller force, but that is a smaller lever arm. And if I let it go, just watch it unwind. Look how much slower it is accelerating. That is a sign that the torque is really small. And this is my way of showing you that the torque depends not just on the force. Most people get that right away. The torque does depend upon force. But the torque also depends on the lever arm. And so that's why I wanted to talk about this one, or at least show you this one, or maybe if you've experienced a bike, or if you've experienced a wrench, or if you've experienced open a door. I'm trying to convince you that torque is more than just force. So I hope I got that through to you. And so that's why the units and the equation have an F and an R. And the unit is a Newton and a meter. So a Newton meter would be the unit for a torque. By the way, in the last chapter on energy, we saw the unit, a Newton times a meter, and we put it together and called it a joule. Do not do that for torque. That's how we're going to distinguish between, are we talking about energy, then we will call that a joule. Or are we talking about a torque? And then if we're talking about a torque, we'll leave it as a Newton meter, not to call it a joule. Otherwise, we can think incorrectly that we're talking about energies, we're not talking about torque. And so this is a whole new quantity. And so I didn't want you to confuse that. Well, like I said, hopefully those illustrations come into play here, because if I go ahead and continue on with this discussion, you might again remember in chapter 3 that we were learning Newton's laws, and of course one of those is force. Or part of Newton's law, I should say, is force. And that's why I wanted to spend a long time talking about torque. Because Newton's second law is the one that is mathematical. Newton's second law says if you take the combination of all the forces, the net force, and divide it by its mass, you're going to get the acceleration. So, in parallel with that, if we're talking about rotations, the angular acceleration is determined by, and in the numerator would be net torque, and in the bottom would be what we're going to call rotational mass. More on that in just a second. But this will give me a chance to come over here to the chart and say, all right, you were asked many times in chapter 3 to get the acceleration of an object based upon the forces. And so you put like two forces together to get the net force, then you divide it by the mass, and then that gave you the acceleration. Now we should have called that translational acceleration. And so I'm saying the same thing. You're going to be asked to get the angular acceleration. Maybe the angular acceleration of this door. And so in order to get the angular acceleration of that door, or in order to get the angular acceleration of this rotating platform, you're going to need to get the net torque and divide it by, we haven't got a chance to talk about this yet, but what we're going to call its rotational mass. And so this gives me a chance to point out that both of them have a net in them. In other words, if I just come up and I'm the only one pushing on this door, then when I say add up all the torques, well, it's just me. But if there's two people pushing on this door, or better still, I've got a nice picture right here. Let's say there's two people pulling on this wrench. The net torque then would be combining the torques together. And so in this case, the two torques are in the same direction. And so this person who's holding the middle is giving a torque, as we calculated earlier, of 10 newtons. And this person, as we calculated earlier, is giving a torque of 20 newtons. And I'll point out, it's worth saying again, both of these people are applying the same force, but not the same torque. Because, again, torque is more than force. So we've got 10 newton meters of torque from this first one. We've got 20 newtons of torque from this second one. If we wanted to then figure out what the net torque is on this bolt, we would add the two together. And so we would say torque 1 plus torque 2, which would be 10 newton meters, plus 20 newton meters. And so this wrench has a total of 30 newton meters. And we're not quite ready there, but if we wanted to then calculate the acceleration of that bolt, we would then take this net torque and divide it by the rotational mass of that bolt and wrench, because they would both be turning, and then we would get the angular acceleration of it. But I just wanted to show you that net torque, like net force, is the combination of all the torques. And so I spent a long time talking about what one torque is. Now I'm trying to get you to see, well, what if I had two torques, three torques? I would just combine them together. Now, you probably wouldn't do this on a bike, unless maybe you were training for some triathlon or something. But what if I was riding this bike with the brakes on? And so maybe before I started to ride, I adjusted the cable up here and I tightened it up so that the brakes are on. And so the net torque would be what I would call torque 1, coming from, I'll say from me. It's actually through the chain, so I push on the pedals, and through the sprocket makes the chain. And so that's what's making it go one way. But the brakes are opposing it. So then I would say minus the torque from the brakes. And so again, hopefully what I'm talking about right now looks exactly like we were doing back in chapter 3, where when we asked what's the acceleration of an object, we had to combine all the forces together. I'm saying the same thing, that we need to combine together all of our torques. And of course, torques could be in the same direction. And let me be careful with that. Same direction, like in this case, means both of these are rotating in a counterclockwise direction. But torques could also be fighting each other They could be in opposite directions. And so just like forces, when they were fighting each other, we subtracted the two to get the net. And so the net torque would be a subtraction of the two. I have a little apparatus that shows it somewhat well here. Let's see if I can set this up here. But if I put maybe a 50-gram brass weight out here and another 50-gram brass weight over here, I'm hoping you can kind of see that this one over here is making this whole thing rotate. Let's see, from your perspective, it would be clockwise. And this one over here is making it rotate counterclockwise. Of course, you don't see that because this one is winning. In other words, what I have here is if I start with them level, okay, I would say then which way is this going to accelerate? And so it ends up going clockwise because the torque from this one, which I'll call the clockwise torque, is bigger than the counterclockwise torque. So these two are fighting each other. And so again, if I wanted to calculate then the acceleration, the first thing I would do is to get the net torque. And since these two torques are fighting each other, I would be subtracting them. But did you notice something interesting here? Again, trying to give you more of an understanding of torque. Did you notice I'm hanging the same amount of mass? Both of these are giving the same force. These are both 50 grams. And even though they're the same force, they are not the same torque. This is my way, again, of coming back to here and saying torque is more than force. Torque is force and distance. And so this one here, if you look carefully at it, I'll put it level again. The distance from the pivot out to here is greater, that's a lever arm, than the distance from the pivot out to here. And so even though they're the same force, that doesn't balance them. They have to be the same torque to balance. And this one has more torque. And so sure enough, it goes that way. And of course, you may ask, well, could you make it go the other direction? Well, sure. I could make this thing rotate counterclockwise instead of clockwise. And I can do that by adjusting the torques here. And of course, one way would be to just move this out further. And now I get more torque from this one than from that one. And so the counterclockwise is more torque than the clockwise. Of course, you may say, well, what if you increase the torque on this side, which you could increase by increasing its weight. So I will take off the 50 and put a 100. Too much. But you can see that now it rotates clockwise. And again, I would say that because I am getting more torque in the clockwise direction. And again, it's torque. It's not force. And so over here I do have more force, but the distance is not as big as that one. It's possible that I get more torque in the counterclockwise direction than in the clockwise. I could do this. I could move this string in, maybe to right about there, and let it, oh, that wasn't quite enough, right about there. Oh, still not enough, right about there. Ah, there we go. Maybe go a little more. And so again, if I start with it level and let it go, sure enough, it goes counterclockwise. And so now I'm getting more torque from this one. And again, notice that this one is less of a weight, less of a force. But it is a big distance compared to that one. And so this force times this distance is a bigger number than this force and that distance. And so the net torque is the counterclockwise direction. In fact, maybe I'll do one more and then move on here, but what would happen if the torques were equal? And of course, that's what we did back here in chapter 3. Way back in chapter 3, I said, well, what if you had two forces on an object, but they were equal and opposite? Well, if they were equal and opposite, the net force would be 0 and there'd be no acceleration. In other words, you would have had balanced forces. And so I'm saying the same thing. If I have balanced torque, I would get no acceleration. So I could come over here, and right now I would say this torque in the counterclockwise direction is a little bit bigger than this torque. So let me just increase the torque by moving the string out. Let me re-level it. Still that one's bigger. Let me move it out a little more. That one's still bigger. I'll move it out a little more. And it didn't go all the way down. It did go a little bit. Let me see if I can level it. And maybe a hair more might be better. There seems to be something a little jammed in there. But it, I think, would be looking a little better right there. There we go. And so the torque making it go clockwise is equal to the torque making it go counterclockwise. And so the net torque is 0. And so again, let me use this as an opportunity to point out the torque is not just the force. If it was about force, then it would definitely go this way. This is more force. But it's got a smaller distance. And so this bigger force at a small distance is then equal to this smaller force at a bigger distance. And so that's Newton's second law. Now, before we can keep going too much with Newton's second law, and I should say Newton's second law of rotation, I pointed out that there would also be in the denominator this thing called rotational inertia. And that's another tough part of this chapter. Let me try to show you that what we call rotational inertia is also a bit more complicated than just inertia. You'll see it well with this rotational platform that I set up here. And so I'll come back to here, and I'll take this string just kind of all the way off. And I'll put it on the big pulley. Okay. So this big pulley will give me the most torque. Let's see if I can lock it into place and lift this up a little bit. And so I'll say it again. This gives me the most torque of those four pulleys because it's got the bigger radius or bigger diameter. And I'll just leave the same weight on here the whole time. And so when I let it go, let's just watch it unwind again. And I don't know if you want to call that fast or not. It's reasonably fast. But watch this. Get a good look at it spinning. Okay, so here it is spinning. Okay. What if I were to actually take some mass off and let it spin? I hope this doesn't surprise you. It spins much easier. That thing spins really fast. Without any mass on here, it just zips along. And that is my way of saying I've reduced its rotational inertia, but I've done it by reducing the mass. And that doesn't usually surprise students. What surprised students is the second part of this. And so let me just put the weights back on. Let me let it go. Okay, so watch it again. Okay, maybe I'll call that a medium speed. Because as I said, if you take these off, that's a fast acceleration. But the important one I want you to see is right here. And I'll just show you that one more time. And watch this. I will not change the mass. But what I will do is change the location of the mass. We often say the distribution of the mass. And in this case, I will move the mass out, away from the rotational axis. Can you see how sluggish that is to get it to rotate? Watch, let me see if I can show you again. Let me wind it all the way up. Okay. So this is the rotation with the weights out. Sluggish. A very small rotation. This is the rotation with the weights in close, and in this case on top of the rotational axis. Watch how much greater it is. And so this little setup is really me trying to say, and so let me continue with this chart. And so here is the translational motion. Here is the rotational motion. We had this idea of mass measured in kilograms that we called it its inertia, and it resists the motion. And we should have said it resists the translational motion, because I'm trying to introduce to you what so far I've called the rotational mass, and I'm trying to get you to see that the rotational mass is more than just mass. Is it partly mass? Yes, and that's why I took these off, and if you take them completely off, this rotates much easier. So that's not usually a surprise that less mass means less rotational mass. But the other part of this, and I'll just put the word distance here, and it turns out to be distance squared. That's not so obvious, but we're going to do an experiment tomorrow where we will actually take a platform, a little different one like this, a little better one that has less friction. And we will then move the weights further out and actually measure how much slower it rotates. And hopefully what you will see in that experiment is that the rotational mass, the rotational inertia, is based upon not just the mass that we have, but where it is located. And as we move it out, we will measure how far we move it out, and we will see that it follows a distance squared pattern. And so we like to do this rotational mass, or maybe I should more accurately call it its rotational inertia. We like to give it this symbol capital I. And I'll put here md squared. But that's not a fair statement in this sense. What if I had something that maybe was a little longer than this? So I'll put this meter stick out here. And the reason I picked this meter stick was the meter stick has its mass, what I would call distributed throughout the distance. So it's not like all of its mass is out here. So I wouldn't want to just take its mass times the distance of the meter stick. I guess what I would want to do is really think of this as a little bit of mass at that distance, plus a little bit of mass at that distance, plus a little bit of mass at the next distance. So a better way of writing this is to say it is a little bit of mass and a little bit of distance squared, and another little bit of mass and its distance squared, and another little mass and its distance squared. And so maybe I should call this mass 1 and distance 1, mass 2 and distance 2, mass 3 and distance 3. And we like to use the Greek letter for summation. It's the capital sigma. And it says, take the mass and the distance squared for that little piece. And so what we like to say is for I equaling 1. And then do it again for number 2, and do it again for number 3, and do it again for number 4, and do it again for number 5. And keep doing this until you run out of little pieces. Now, here's where I'll kind of hit the pause key on the math. Because this summation, for some of you who've gone this far, would actually be an infinite number of terms as I cut these thinner and thinner and thinner and thinner. And so how do I add up an infinite number of little pieces? And that mathematics is part of calculus. It's called an integral. And so some of you have done that and some of you have not. And so that's why for this class, we'll just mostly say, hey, this is the moment of inertia. We're not going to try to actually calculate it until you get into Physics 121. Because the prerequisite for Physics 121 is learning how to be able to do something like this. And this is just one of many examples where calculus will become very useful. So at this level, we can't really calculate what the rotational inertia is of this meter stick. And that's fine. We're not there yet. We will when we get to chapter 10 in Physics 121. So for some of you, that's next fall. You will actually do this integral. For others of you, you still need to take calculus next fall. That's fine, and then we'll do it next spring. So I'm going to put this equation on the board only because this will help me determine what the units are. And so the units would be kilogram and then meter squared. And so that will help me over here in this table to say, when it comes to rotation stuff, how does that compare to translational stuff? And so we're going to use the symbol I to distinguish it from the M. And the units are kilogram meters squared. And I needed to justify that to you. I needed to explain why the units have a mass and a distance squared in them. And so my whole point here is to try to convince you that rotational inertia is more than just inertia. It is more than just mass. It is mass and distance. And it's not even distance, it's distance squared. And so even though you guys are not ready to do the calculations for this, you are at least ready to understand the concept that to get something to rotate requires a torque, and torque is more than force. And what's stopping it from rotate is its rotational inertia. And at that, rotational inertia is more than mass. It is mass and distance. And so this is, again, a long way of me trying to point out that I think rotation is a little bit harder than translation. See, torque is more than force. And inertia is more than mass. It's mass and distance squared. And so when we start working with our problems here, we have to think about not just what is the mass of the object, but where is that mass located? And so something that like I did earlier, as simply as taking this mass and moving them out, that configuration right there is harder to rotate than this configuration. That's the big thing of this chapter. Rotational inertia is more than mass. Torque is more than force. But conceptually, they fit the same idea. So hopefully if you conceptually know what mass is, you know what rotational inertia is. Conceptually, if you know what forces make them translate, then torques make them rotate. And that's really the hardest part of this chapter. There's a couple of other things in this chapter, but that whole idea here of Newton's second law, where torque is more than force, and rotational inertia, I should have put inertia, not mass. Rotational inertia is more than mass is an important and often difficult concept for students to get. And again, that's why we're going to do a lab on it tomorrow. We're going to hook these up and we're going to rotate it. And that lab's really good. It's got two parts. And the two parts, not surprising, are based upon showing you how torque is a little bit different than force, and also trying to show you how rotational inertia is a little bit different than just regular mass. So, with all that in mind, I think you can see this more in an experiment or two, because again, it's kind of tough, I think, to really get that idea of rotational inertia being more than just mass. And so it's why we built these two rods. And we said if you look at these two rods, they're plastic tubing, that's true. But inside the plastic tubing, and so we made it a clear plastic tubing, we've put little tiny lead shot in here. And we actually put the same amount of lead shot. As I hold it up to you, the lower one, this one here, the lead shot is all in the middle of the rod. But in this one, the lead shot is out near the edges of it. And so we just cut the lead shot in half and moved half of it out to here and half of it out to here. And so these two rods actually have the same amount of mass. Now you can't really do this because we're not face-to-face, but in a face-to-face class I encourage students, hey, if you want to hang after class and try this, it's kind of fun. Take this rod, hold it in your hand, and try to change its rotational state. In other words, move it clockwise, counterclockwise, clockwise, counterclockwise, clockwise, counterclockwise, and see how quickly you could do that. All right. So in my case, I can go about this fast. All right. Try it with the other one. Okay. Now remember, the other one has the same mass. But here's the point, the mass is at a different location. And you can see if I'm holding it in the middle, the mass is further out. And so if you try to go clockwise and then counter, clockwise, this is about as fast as I can go with it. And I have a real hard time changing its rotational state. And I have that hard time because I would say its rotational inertia is much bigger. Not because it has more mass, but because the mass it does have is further out. And so I feel like I've spent a lot of time here, but hopefully I was well invested time, and you guys are getting the idea, because I just know from the past it's these two things about rotation that students have really struggled on. And so I'll say it again, torque is more than force. It's a force and a lever arm. And also what I'm trying to dwell on now, rotational inertia is more than just mass. It is where it is located. And again, that's why that little experiment, which too bad it's not face-to-face, so you guys could actually try this. It's real impressive when you get to try it. But tomorrow's lab, as I said, you'll see the same thing when we actually run some numbers. We actually take these weights and we keep moving them out further and further and further and further. Now, it's a little different setup. And we have square weights, and we move them out further and further and further. And you'll see, hopefully, in that lab, that the rotational inertia keeps getting bigger and bigger and bigger and bigger. I have another fun one that, again, just kind of illustrates the same point. It's kind of this race down the hill. And so I've got this little incline here. And if I put this one, let me call it the hoop, at the top of the hill and let it go, it rolls down the hill. Of course, gravity is pulling it down the hill. This one here, let me call it the disc. Again, I can put it at the top of the hill and let it go, and it rolls down the hill. And these objects are almost the same. I think you can see that they have the same diameter. You can even see they're the same color. What you can't tell on video is they have the same mass. I probably should have brought a scale out here, but these are both 612 grams. This one and this one. Now, this one is made out of metal. And maybe you can even hear it on there if I... Metal versus wood. Okay? Because I know what you can see is where they are different is this one is solid all the way through. That's why we call it a disc. And this one is hollow, which is why we call it a hoop. Okay, but that being said, what that would mean is that even though they have the same mass,